Welcome to video lesson 1 on chemical kinetics. We're going to talk about the reaction process first, and when we are going to be talking about kinetics, we're basically going to be talking about the rates at which they happen, because some reactions happen very quickly and some are very slowly. So in this example we have iron rusting, which takes time, and you of course know that natural gas burns very quickly when ignited. So those would be the difference in their reaction rates. So that is what chemical kinetics is the study of rates. The reaction rate is basically the rate of disappearance or the rate of appearance of the products. So we can disappear the reactants or we can appear the products, and it really and truly depends on what's easiest to observe, and usually we're going to have that in units of molarity per second. Remember, big M is molarity and then little s is second, so that's going to be our units. Today we'll not be doing the math part of this unit. That'll be lesson 2, and so today we're just going to learn about the things that affect the rates. So the first thing that we are going to talk about is something that's very important. It's called the collision theory. And there are 3 things that are included in the collision theory, and that is 1, total number of collisions. So we're talking about the particles colliding with each other, the orientation of the particles, in other words, they have to be lined up correctly, and if there's enough energy for the reaction to happen. When all of these conditions are met, we call these effective collisions. And so the more effective collisions you have, then the more likely you are to have a chemical reaction. So we're going to talk about each one of those things a little bit more extensively. So we're going to talk about the orientation of particles first. For a collision to be effective, the reactant molecules have to be oriented in the correct manner. So think about something that is a polar compound. If it's slightly positive on one end, slightly negative on the other end, in order for them to react, you can't have the 2 slightly positive ends lined up because they will repel each other. So you would need to have basically the slightly positive end pointing towards the slightly negative end so that the reaction could happen. Now that's a very simplified version of that, but it helps you understand that. So I have a visual. And it shows you that if it's an ineffective collision, they don't line up and it doesn't happen. But if it's effective, then in this case this would be a single replacement. In this case, A would replace B and form a new compound. And here's another example with the HI molecule. In order for it to react, the molecule needs to be lined up correctly with the next molecule. Okay. The next thing is minimum energy. Okay, potential energy diagrams, we talked about that last unit, and we showed you if it was endothermic, exothermic, whether it was products having more energy or less energy. But the top of that energy diagram is going to be important too. They are representing the energy pathway of the reaction. At the top of that, and you have the graph on your paper, and I'll show it to you on the next slide. At the top of that hill, if you will, is what's called the activated complex. And it's a temporary complex, and it's the point at which we have reactions, the bonds are breaking and new bonds are forming. The activation energy is the energy needed to form that complex, and it is the top of that. If the reaction does not have enough energy, the reactants will reform and you won't get any products. If you do have sufficient energy, then you will form the products. So let's look at that a little bit so that we're on the same page here. So if we look at this, we're going to label some stuff, or at least point out some stuff. Up here is our activated complex, okay? This activated complex would not show up in the final reaction. When we see a final reaction, we see the net overall change, what happened from the products to the reactants. But in fact, there's some stuff that's going on in the middle that we don't always see. And when we get to the last lesson of this unit, which is reaction mechanism, that's when we'll kind of discuss that a little bit. Okay, so here we have the reactants, CO and NO2, and we're going to react them, and it's going to form CO2 and NO. So the forward is going to be an exothermic reaction because it lost energy. But if I was to reverse that reaction, and let's go ahead and write that down on your graph so you understand the reverse reaction. If I was going to reverse that, that means the reverse reaction would be CO2 plus NO is forming CO plus NO2. And of course, this right here is the forward reaction. So of course, if I reverse that reaction, it's no longer exothermic, it would be endothermic. Okay? But I want you to look right here. The difference between the reactants and the top of that energy is called the activation energy, and that would be the activation energy of the forward reaction. Okay? The delta H, which was enthalpy from last unit, is the difference between the reactants and the products. So this part right here is not included in the delta H, but it is part of the activation energy. Okay? So I'm going to clear that slide and then talk about the reverse reaction. So if I was going to reverse that reaction, I want you to excuse me, I want you to think about it. If I reversed it going the other way, then my reactants are going to have more energy than my products. So it would kind of look like that. So then my this right here would be my activation energy, because it's the difference between my reactants and the top of the hill, but then this right here, from here to here, would be my delta H. Okay? And so they're kind of showing that here on the same graph, but I wanted to draw it separately so that you could see that I would just flip that around. But the activation energy is going to be the difference between the energy of the reactants and the top of the graph. The delta H is going to be the difference in energy between the reactants and the products. So delta H doesn't necessarily go all the way up. Okay? Here we have the same thing, showing it both side by side, so you can kind of look at that. This is not in your notes, but there is room if you wanted to stop the video and draw it in real quick, so that, excuse me, so that you could have that, again, where that red is, that's going to be your delta H. In the first case, it's energy released because it's an exothermic reaction. In the second case, it's going to be energy absorbed because it's an endothermic reaction. And just to make note, up here would be where that, up here is where that activated complex would exist. Okay? So next thing is the physical, oops, did I miss something? Nope, I didn't. Okay, so some things that will affect the reaction rates. We have the physical state of the reactants and their surface area. In other words, the nature of the reactants. Is it a powder? Is it a solid? Is it a big chunk of something? Also, is it a solid, liquid, or gas? The temperature is going to affect it. Presence of a catalyst, and concentration of reactants. And so we're going to talk about each one of those a little bit more extensively. So nature of the reactants, their rates depend upon the reactivity of the reactant. Makes sense. Ionic reactants occur almost instantaneously. Why? Because there is no electron rearrangement needed. They have already exchanged their electrons, and so they're going to be very reactive. Molecular compounds, which of course are covalent bonds where they're sharing, they take a little longer to react because they've got to decide how they're going to share those electrons, and so they take a little bit longer, so they're a little bit slower. Increased surface area, which means, of course, smaller pieces, and that means we crush it because that means there has a larger surface area. Some people got confused on one of the last tests, and they thought, oh, big chunk means larger surface area. It does not, because remember, when you have a big chunk of something, only the outside of that chunk is going to be reacting, whereas if I take that same amount and crush it up, all of that could be reacting. Stirring, it kind of falls in here a little bit because by stirring it, we're going to be removing the particles that have already reacted and introducing them to a fresh solvent. So like if I was going to make some Kool-Aid, I don't just dump the sugar in there and pour the water, I stir it, and that's because I'm introducing my water to my sugar and Kool-Aid, and so it mixes up quicker. Okay? Here's just an example of surface, oh, well, I spelled that wrong, I need to fix that. Surface area, I guess I got a little ahead of myself, and they're just showing you, again, if I had this big clump, like I have here, only these outside particles would be reacting, okay? But if I break it up, now I've got the same amount, all these outside particles are reacting, and so it has a larger surface area, which is going to make a faster reaction. Temperature. Increasing the temperature typically increases the rate of reaction, and that is because by increasing the temperature, a greater proportion of molecules will have the minimum energy. So heat them up, speed them up is what we're going to say here. So if I'm increasing the temperature, I'm increasing the energy of the particles, because remember, temperature and kinetic energy directly related. So it tends to give it enough energy, or gives more of the particles energy to have those effective collisions. Okay? What it does not do when I increase the temperature, it does not affect the orientation of the particles. Okay? It does affect the energy, but it does not affect the orientation of the particles. You need to know that it takes energy to break the bonds, so that's going to be an endothermic process, but energy is released when the new bonds form, which is exothermic. And if more energy is released when new bonds form than it took to break the bonds, then you would get an exothermic overall reaction. So here is a graph of what temperature does. T1 is the blue graph. T2 is the second one, which is going to be where the second temperature, I've increased the temperature basically, okay? And so if you look at fraction of collisions, the number of collisions that have enough energy, and of course this is that activation energy, so this is that point at which the reaction would happen if it had enough to overcome it. So you see it increases the amount above here that would actually form, and that's because they have more energy, so they are more likely to overcome that that activation energy. The presence of a catalyst, and of course you probably remember this from biology. A catalyst is something that increases the rate. In biology we call them enzymes in our body, but basically what happens is the catalyst lowers that activation energy, and so it does not affect the overall delta H, but what it does is it lowers the hump, if you will. Okay. The opposite of a catalyst is an inhibitor, and that is the opposite. It would actually create a higher activation energy, and so the reaction would be less likely to have it happen. And that's what preservatives basically are that we have in our food, and they, or even some other things that we don't want to go bad as quickly, so we put a preservative in them, and so that reaction is inhibited. So here is what it looks like if you have the difference between the catalyst and not. So the dark purple line is the activation energy of the reaction normally. The dotted line is the presence of a catalyst. So what it does is it lowers that activation energy. But what I want you to notice is it does not change your delta H. You still have the same difference between your reactants and your products. So if you are drawing a graph and they ask you to show it with a catalyst in it, basically you're just going to draw a smaller hump. So notice that the reactants are starting in the same place and their products are ending in the same place. So the only thing that's going to change is the size of your activation energy hill. Okay? So that's something important to be able to understand. The concentration of the reactants also makes a difference. This is kind of a no-brainer. Increased concentrations means I have more stuff to collide. Okay? So if I have, say, let's say I have something that is a 0.25 molar concentration, and I have something that's a 2.5 molar concentration, well, the rate will be faster for that 2.5 because it has more stuff to collide. So increased concentration will also cause an increase in collisions. Okay. For gases, we are going to treat increasing the pressure as an increase in concentration. Okay, so that's going to take us back to, remember that relationship from gas laws. Pressure and volume are inversely proportional, right? So if I increase the pressure, I'm decreasing the volume. Okay, and so when I decrease the volume, now I have the same amount of particles, right? Less volume, and that is moles over liter. So if I am decreasing that, I still have the same amount of moles. I didn't do anything to change that, and so now my concentration would be stronger because I have a smaller volume. Okay, so I want to make sure you understand that. Okay, so here's just a visual. Obviously, if I have more particles, there are more collisions, and so the reaction rate is greater. That's kind of a duh, right? All right, that is the end of this lesson. I'm going to see if this works for you. Here's a cute little video. It's a TED Talk. Can't go wrong with TED Talks. And it's just kind of a way to help you remember this collision theory. So I'm going to play that, and that is the end of the lesson. If for some reason this doesn't work, I'm going to ask you to log out, and I did link this on the canvas, and you can just click on it real quick. But hopefully it works here, and you don't have to worry about it. All right. Maybe it's not going to work. It is not. I tell you what. Oh, there it goes. Yay! It is going to work. All right, let's expand that. And, well, that didn't work, but we'll do it this way. I'm going to make this work so y'all don't have to worry about it. And here we go.
Meet our chemist, Harriet. She has a chemical reaction that needs to occur more quickly. Our chemist has some processes at her disposal that can help her speed up her reaction, and she knows of 5 ways. And to remember them, she thinks back to her days as a high school student, and the day she got a date for the dance. Harriet was in high school studying between classes. She had lost track of time and was going to be late to class. Unbeknownst to her, Harold, who was just around the corner, was running late too. They both sprinted to class, and as it happened, sprinted directly into one another. Now, this was no small collision. They ran squarely into one another in such a way that he knocked the books right out of her hand. "I'm sorry," he said. "Let me help you with your books." He kindly helped her recollect her belongings and politely offered to walk her to class. And you'll never guess who went together to the dance later that year. Yep, those two. So as we can see from this example, the key to getting a date for the dance is to collide with someone and knock the books out of their hands. Now, you're probably already aware that not all collisions lead to dates for the dance, thankfully. The collisions must have 2 important characteristics. 1, correct orientation that allows books to be knocked from one's hands, and 2, enough energy to knock the books out. Shortly after this incident, Harriet decided to tell me, her chemistry teacher, all about it. I noticed some interesting parallels between her story and chemical reaction rates, which happened to be what she was studying in the hallway the day of the collision. Together, we decided to set out on 2 missions. Harriet wanted to help all chemistry students and chemists remember how to speed up the rate of chemical reactions, and I, being the nice guy that I am, decided to make it my mission to help create educational environments in which more book-dropping collisions can take place to increase future chemists' chances of getting a date for the dance. In order to facilitate this improved dance date-getting process, I propose 5 changes to all schools that parallel Harriet's 5 ways to increase chemical reaction rates. First, I propose that we shrink the size of the hallways. This will make it more difficult to safely navigate the hallways and will cause more collisions than in larger hallways. And by increasing the number of collisions, we increase the likelihood that some of those collisions will have the correct alignment and enough energy to create a date for the dance. Now, chemically speaking, this is equivalent to lowering the volume of a reaction vessel or a reaction mixture. In doing so, the individual particles are closer together and more collisions will occur. More collisions means a greater likelihood that collisions with the appropriate energy and configuration will happen. Second, I propose increasing the overall population of the school. More students equals more collisions. By increasing the number of particles available for collision, we create an environment where more collisions can take place. Third, we must reduce the time allowed between classes. Heck, let's just cut it in half. In doing so, students will need to move more quickly to get from one class to the next. This increase in velocity will help make sure collisions have the appropriate amount of energy necessary to ensure book dropping. This is analogous to increasing the temperature of the reaction mixture. Higher temperature means particles are moving faster. Faster moving particles means more energy and a greater likelihood of reaction causing collision. Fourth, students must stop traveling in packs. By traveling in packs, those students on the outside of the pack insulate those in the middle from undergoing any collisions. By splitting up, each student has some more area exposed that is available for a collision from a passing student. When particles travel in packs, the surface area is very small, and only the outside particles can collide. However, by breaking up the clumps into individual particles, the total surface area is increased, and each particle has an exposed surface that can react. Fifth, and finally, we hire a matchmaker. Is this colliding and book dropping too violent? Is there an easier way to get a date that requires less initial energy? Then a matchmaker will help with this. The matchmaker makes it easier for a couple to get together by coordinating the match. Our matchmaker is like a catalyst. Chemical catalysts function by lowering the activation energy. In other words, by lowering the energy required to start a reaction. They do this by bringing two particles together and orienting them correctly in space so that the two can meet at the correct configuration and allow a reaction to take place. So, to sum up, if a future chemist wants a date for the dance, he must collide with another person and knock the books out of their hands. And if a chemist wants to make a chemical reaction occur, the particles must collide in the correct orientation with an appropriate amount of energy. And both of these processes can be accelerated using the 5 methods I've described.